Oh, welcome back. Last time we dealt with a problem, an arc length problem that required us to take the derivative of the inverse cosine. This time, in this video, we're going to take a look at the derivatives of the inverse sine, the inverse tangent, and we're also going to take a look at some triangular relationships that can be helpful, that can simplify the solutions for derivatives of inverse trig functions. So that's on tap for today. In this video, just a reminder from the last time we went through this derivation in order to get the arc length. The incremental arc length associated with an incremental height, we're asking arc length was the distance out along the surface from a point of directly beneath a point of observation at some elevation. In this case, we used 100 meters. And at 100 meters, we found that the change in the distance out along the surface for a 1 meter change in elevation, assuming that you're standing on a hill that's about 100 meters high, would be about 178.462 meters. So, times 1 meter. So the arc length, in a simplified form, we assume that h is much, much smaller than r. We ignore h. That simplifies the problem. And we showed that that really didn't make too much of a difference. These two numbers are, for all practical purposes, very close to each other, almost identical. Got about 0.004 of a meter difference there. And also in an earlier problem, we showed that the change in the line of sight with an increase in elevation turned out to be 178.468. dh in this case could be 1 meter, so 178.468 meters would be the increase in the line of sight. So the increased distance that you could see with an increase in your elevation of 1 meter, you gain 178.468 meters of viewing distance, and these numbers are all very close to each other. But we can see that ds is just a tiny bit less than dl by about 6 thousandths. So that's just a review. We had to use the inverse, we had to use a derivative over the inverse cosine in order to get this solution. So every now and then you have to use these kinds of derivatives come up, and you need to use them in order to solve problems of interest. So let's take a look at the inverse sine. Let's start with our basic definitions. We've got the sine of theta is equal to x. So the inverse sine of x is equal to theta. Then we take this chain rule differentiation approach. First we take the derivative of the sine of theta with respect to theta, then the derivative of theta with respect to x, and this is what we're after. Theta is the inverse sine in this case. And then we have dx by dx, which is just 1. So the derivative of the sine of theta with respect to theta is just the cosine of theta. d theta dx is equal to 1. And we have d theta dx is equal to 1 over the cosine of theta. So, d theta dx is equal to 1 over the cosine of theta is equal to 1 over the square root of 1 minus x squared. However did we get this? Well, remember the last time we used an identity. That identity was that the cosine squared of theta plus the sine squared of theta is equal to 1. Well, we solved that for the sine. This time we're solving it for the cosine. We find that the cosine of theta is equal to 1 minus the sine squared of theta to the 1/2 power. But sine of theta is equal to x. So that gives us this 1 minus x squared to the 1/2 power. Okay? So let's take a look at one more. Quickly we'll do the inverse tangent. And we're going to be using these triangles. I'll tell you a little bit more about that. We've been using these triangular relationships. And again, we start with basic relationships here. We've got tan theta is equal to x, and theta is equal to the inverse tangent of x. We do the chain rule differentiation. Differentiation of the tangent of theta with respect to theta, d theta dx. This is what we're after. This is the inverse tangent, theta. dx by dx is just 1. The derivative of the tangent of theta is secant squared theta, or 1 over the cosine squared theta. d theta dx is equal to 1. So that gives us that d theta dx is just equal to the cosine squared of theta. But just as we were before, what can we do with cosine squared of theta? How can we relate that back to the tangent of theta? And that's where these triangles come in are useful. We can define a triangle like this. We can define its sides such that we know that the tangent is defined as the side opposite over the side adjacent. So we'll just let the side opposite equal tangent of theta. Side adjacent equal 1. So tangent of theta is equal to tangent of theta. But that makes the hypotenuse the square root of 1 plus tan squared theta. Okay? So we have tangent of theta is equal to x. We have that the cosine of theta, side adjacent over the hypotenuse, is going to be 1 over the square root of 1 plus the tangent squared. So the cosine squared of theta must be equal to the cosine squared, or 1 over 1 plus the tan squared of theta to the 1/2 power squared, which is just 1 plus tan squared of theta. So since tan of theta is equal to x, we have d theta dx is equal to cosine squared of theta, which is equal to 1 over 1 plus the tangent of squared theta, or 1 over 1 plus x squared. So these triangles are useful. Let's just take a minute and look at a couple triangles that we've already used. We define the sine of theta as the side opposite over the hypotenuse. Sine over 1 is sine. Cosine of theta, side adjacent over the hypotenuse, just the cosine. So we get sine squared theta plus cosine squared theta is equal to 1, just using the Pythagorean relationship. And the triangle that we just used, tangent of theta is equal to the side opposite over the side adjacent. So we get tangent of theta is equal to tangent of theta over 1. It's equal to the tangent of theta, but the hypotenuse then must be equal to the square root of the sum of the squares of these two sides. So now if I want to know what the sine of theta is in terms of the tangents, that would just be tangent of theta over the square root of 1 plus tan squared of theta, right? And you can see where that would be potentially useful. So cosine of theta is just 1 over the square root of 1 plus the tangent squared of theta. Okay, so here's one for the sine. Sine of theta, side opposite over the hypotenuse. Sine over 1 is equal to the sine, but that makes the side adjacent equal to the square root of 1 minus the side opposite squared, sine squared of theta. So we have the tangent of theta equal to sine of theta over the square root of 1 plus sine 1 minus sine squared of theta. The cosine of theta would be equal to side adjacent over 1, square root of 1 minus sine squared of theta would be equal to the cosine of theta. And so I think you can see where these relationships, if you want everything in terms of the sine or the tangent, if you want all your trigonometric relationships in terms of a particular trigonometric function like the sine or the tangent, then we can develop triangles like this. So as an exercise, here's a triangle. Develop a triangle to show your trig functions in terms of the cosine. Well, we know the cosine is the side adjacent over the hypotenuse. That would be the cosine. This side must have a length equal to the cosine of theta. So have a look at that. That should be pretty easy for you to do using these examples here. Next time around, we're going to get into integral calculus. So see you then.